So let's do an example of a hypothesis test. In this case, we're going to do what's called a single sample t-test. It's one of the simplest hypothesis tests you can do. And this is a pretty useful tool. We use it in a situation where we have a population about which we know a lot of statistical data. An example would be somebody who produces a lot of aluminum, or the same type of aluminum, and they've done things the same way for a long time, and they have a lot of data concerning their averages and standard deviations. They know how their population behaves because they've collected a ton of data. If we make a change, we want to conduct an experiment, we don't often have the resources to establish a new population data. We're not going to produce this for the next 3 years and then determine whether a change has been made. We want to know pretty quickly with a small sample. So we want to compare a small sample to a known population behavior from before the change. And so in that case, we're going to take a single sample and we're going to use a t-test to compare that single sample to the original population to see if there was a change in average value. T-tests generally deal with a change in average, not variance. So in this example, let's say we increase the temperature of our quench water a little bit, and we want to know whether it affected the average ultimate tensile strength of the product that we're making. In this case, the way that we've structured this question, a change either positive or negative would denote a difference that we're interested in demonstrating. Therefore, we're going to use a two-tailed t-test because it could go either way. So here's the basic rundown of what we do. First things first, we take a sample of UTS measurements. We make our change in our process, and then we're going to get our sample of ultimate tensile strength measurements after the change. We're then going to compare the sample mean, x bar, to the previous population mean, mu naught, which is just a way of saying the original mean. And we want to know how far apart they are, kind of in terms of standard deviations. In other words, how far are they apart relatively? Based on that and the t-distribution that has to do with the probability related to that difference, we're going to determine the probability of obtaining that sample mean if there was no effect. In other words, if this came from the same population and I know the t-distribution governs the probabilities associated with that, what's the probability that I had a sample mean this far away from the actual population mean if there wasn't any effect by the quench water? If that probability is very high, then we don't have any evidence of a change in the new mean from the original mean. In other words, we can't show that there's a difference between the two because it's pretty highly probable that we would have obtained that result if there wasn't any change. If the probability is low, however, then there is evidence of a change in the new mean from the original population mean. To make that determination, we're going to use what we call the t-statistic. And we're going to basically compare the difference in means to their relative standard deviations. And based on that and the normal curve and the t-distribution, we can determine the probability that we would have obtained that result. The t95 that we're going to use to make our determination, what we call the critical value, is the t-value that denotes a 95% probability that we will fail to reject the null if it truly should not be rejected. In other words, if our t-value, if our t-value is less than the critical value, then the two means are too close together to be able to say that there was a change. If our t-value is greater than the t95, then we know that the difference between those two means is significant enough to make that determination at a 5% level of significance. In other words, there's a 95% probability that we would fail to reject the null if it should be rejected, or should not be rejected. The 5% level of significance is kind of saying the other thing. It's a 5% probability that we will reject the null if it truly should not be rejected. So there's a 5%, if we use T95, in other words, if we use a 5% level of significance, that establishes the probability that we are incorrect in rejecting the null. And so you just denote, okay, am I all right with a 5% level of significance? Maybe I want a 1% level of significance. Maybe I'm okay with 10%. That threshold changes depending on how high of a probability you're willing to accept that you're incorrectly rejecting the null. So let's take a look at this. Our null hypothesis here is that the ultimate strength was not affected. In other words, the new mean is equal to the original mean. The alternative hypothesis is that the ultimate tensile strength was affected, whether greater or less, whether the new mean differs positively or negatively, that there is a difference. So what that means is we're going to use a two-tailed test. And our test statistic, T0, is used for the comparison of a small sample to a population mean. Because I'm not, again, going to take 3 years of data before I do this experiment. I'm going to do this experiment and take a few data points and then compare them to my well-known data. The equation for this, which you can get out of just about any statistics text, is the difference between the two means here, x bar, which is our new sample mean, minus the original population mean, divided by s over the square root of n, which is basically our standard deviation in the sample mean. In other words, here's how much variation we expect from one sample mean to the next. The more points I take, the higher the number of points I take, the easier it is to show a difference between these two means. So our original population mean, let's say, was 48 KSI. And I take 5 measurements, and they have an average of 46.1 KSI and a sample standard deviation of 4.72 KSI. So we have 46.1 plus or minus 4.72 is the standard deviation. That's pretty wide standard deviation. We have a coefficient of variance here of almost 10%, actually a little bit more than 10%. So we get our T0 value, which is basically how far apart are our means in terms of standard deviations. It's a really simplified way of saying it, but that's more or less what's happening here. And so we have the difference between the two means divided by the standard deviation over the number of data points we took, and we get a t-value of 0.9. If we look up from the t-table, the critical t-value is 2.776. So in order for us to show a significant change, we would have to have 2.776 effective standard deviations between the new mean and the old mean to show a significant change. As a result, this isn't a very high number, certainly not high enough to be beyond this critical standard, and so we fail to reject the null hypothesis. We cannot show with this data that there is a significant change. The p-value, which is another calculated value you'll get often out of statistical calculators like Minitab or Excel, the p-value is the level of significance we would have to accept in order to reject the null hypothesis. In other words, we would have to be willing to accept a 42% probability that we would be incorrectly rejecting the null in order to reject the null. I mean, the only, so this is the probability based on this data that we would be incorrectly rejecting the null. And that's just, it's way high. 1 in 2, that's flip a coin. We can't make a substantive statement based on that. So there are different test distributions and statistics that we would use to do different hypothesis tests. If we're doing differences in means, in other words, if we want to see a change in an average value, then we use a t-distribution. And here are some example questions you might ask. If we're looking for differences in variance or standard deviation, was there a change in the standard deviation, then we use the F distribution. And those are the two main ones. There are a number of other probability distributions and hypothesis tests out there, but these are the two tests that kind of dominate the type of work that most engineers are going to do. If you need more information, there are a couple of good texts on the topic. Understanding Design of Experiments by Del Vecchio is a good one. You have Engineering Statistics by Montgomery. That was your textbook in ISC 3200. And there's also a pretty good text, Statistics for Engineers and Scientists by Navidi, which is also a pretty good resource with good problems.